All right, in 6.1.0 notes, we're looking at the introduction to stoichiometry, what it is, and then a couple calculations, a one step and a two step. You will need a calculator and you will need a periodic table. So if you don't have that, pause this and grab those first. All right, stoichiometry is actually a really practical branch of chemistry. It is taking the balanced equation and the mole and combining it. So there is a lot of math in this, but it's not too much different stuff. We are actually going to use some previous skills in here. So stoichiometry is a big word. If you broke it down, stoichion, this first part is in Greek. It means element, and then metry means measure. So you're measuring elements. So essentially, what you're doing is you're taking a balanced equation. If you consider that like a recipe, and it's balanced, obviously if we have it in the right proportions, we can figure out like, so how much reactant, in this case aluminum oxide, do we need to create so much oxygen or aluminum, or how much aluminum will be produced with like certain amount of aluminum is given, how much oxygen will be produced along with it. So we're just using proportions and we're using our molar masses to figure out different amounts. So we have what's called a mole ratio that is in every single stoichiometry problem, and that's why it's crucial to have a balanced equation first going into any kind of stoichiometry problem. Without that, you cannot do stoichiometry. We also have conversion factors, so we're going to be utilizing some dimensional analysis. I will be using that. However, if you find just setting it up and multiplying and dividing it, just like we did before, you can do that as well, as long as you show your work. So we're going to be always having the step of the mole ratio, and you get that mole ratio from your balanced equation. So you can see if you are comparing, like, for example, aluminum oxide and oxygen, it's 2 moles. These coefficients, as a reminder, mean moles. So 2 moles of aluminum oxide over 3 moles of oxygen, or you can flip it and have 3 moles of oxygen on top and 2 moles of aluminum oxide on the bottom. And that is, when you're setting up your problem, however you need to set it up to cancel out what you need to get rid of and what you're trying to solve for. And by the way, in stoichiometry, we can compare any two substances. So in this case, we only have one reactant. We can compare the reactant to a product, or we can compare two products to each other. Or if, say, we had two reactants, we can compare two reactants to each other. So it doesn't matter. Anywhere in that equation, you can compare substances. Okay, so let's take a look at this equation, which is balanced. So 2 moles of mercury oxide are decomposed into 2 moles of mercury and 1 mole of oxygen gas. So if we are going to write all our possible ratios, we can start out with comparing like these two first, okay? So 2 moles of mercury oxide over 2 moles of mercury. And of course we can flip that. So you can have 2 moles of Hg on top and 2 moles of HgO on the bottom. Another one, we can compare HgO and oxygen. So we can do 2 moles of HgO over 1 mole of oxygen, or we can flip that. And lastly, we can compare HgO and oxygen. Oh, I did that already, sorry. We can compare HgO and oxygen. So 2 moles of Hg over 1 mole of oxygen, or flip it. So I know it kind of looks similar, but these are all different. And so we have 3 different mole ratios, but we can express them 6 different ways. All right, overview. This is our mole map. This is like the whole thing of all of our equations or calculations. We're going to do 2 out of 4 today. So we are going to do moles to moles, which is the simplest and the shortest. It's a 1 step, and this step is in every single Stoich problem. And then we're going to add on mass to our second type of calculation. So this one is right here, this little piece. This is what we're going to use right now for now. We do have to have a balanced equation, which in this case we do. 2 moles of potassium chlorate decomposed to create 2 moles of potassium chloride and 3 moles of oxygen. So our question is, how many moles of potassium chlorate are needed to make 15 moles of oxygen gas? So I'm going to rewrite my given, and notice I'm writing my formulas. That is really something that I emphasize that you should do, because it's really easy to get confused what you're talking about, especially when you're doing moles over moles, which is the same unit. We're talking about different things in the equation. So 15 moles of oxygen, and I'm going to set this up with dimensional analysis, and I'm going to look for the mole-mole ratio between oxygen and potassium chlorate. So this is oxygen, this is potassium chlorate. On the side here, I'm just going to rewrite my mole ratio, and I can write it like that. But in this case, I want to flip it because I want oxygen on the bottom. So by putting oxygen on the bottom, I can cancel it out. It's moles of oxygen are canceled out. And now I'm done. I wanted moles of potassium chlorate. So 15 times 2 is 30, divided by 3 is 10. We don't need to put that in our calculator. Okay, 10 moles of potassium chlorate will be needed if I want to produce 15 moles of oxygen. And that should make sense because in this equation, it says 3, and I started out with 5 times the amount. So I really need 5 times that mole ratio of that reactant in order for that to happen. So it's all proportional. All right, go ahead and pause this. This is another practice problem. It has a different equation, but it's the same process. See if you can solve it using the model from above. All right, if you need a little more extra instruction or to see the answer, here you go. So you have 14 moles of H2. That is what we're starting out with. Okay, and we want to know how many moles of ammonia, which is this. So these are the two things that we're working with. We're not working with hydrogen at all. It's just not part of the problem. So we want to do a mole-mole ratio. Okay. Oh my, I'm just kidding. We are doing hydrogen. We are not doing nitrogen. That looked like an N to me. All right, so we are looking at these two. So we can do 3 moles of H2 over 2 moles of NH3, or remember we can flip it. And in this case, we do need to flip it because H2 needs to be on the bottom. Okay, so in our calculator, we will type in 14 times 2 divided by 3, and you get 9.33 moles of ammonia. And that is it. Okay, here's one more, but this is going to take it a step further. You have to write the equation first, the combustion reaction, which is oxygen as a reactant, and you have tricarbon octahydride. So if we have oxygen with it, you could predict the products and then balance it first. That is essential before we can do any Stoich problem. All right, so our two products are carbon dioxide and water. We do need to balance this. Oops. So we have, I would always suggest leaving oxygen to last to balance because it's appearing in multiple places. So focus on carbon and hydrogen. Carbon, there's 3 here. There's only 1 here, so we need a 3. That balances it out. Hydrogen, we only have 2. We have 8 on this side, so if we put a 4 here, we balance that out. Now we can fix the oxygen. So we have 3 times 2 is 10, plus 4, 3 times 2 is 6, plus 4 is 10, so we need a 5 here. All right, now that we're balanced, we want to know moles of carbon dioxide, and we're starting with oxygen gas. So it's helpful to kind of focus on whatever you need to. We're not working with these two things. We're only working with these two. So we'll start out with our given 4.25 moles of O2. And you can pause this and try this on your own since this is a third type of problem, or third example of the same type of problem. We are going to do a mole-mole ratio first. I'm not going to write it out over here. So we're going to get rid of, in order to get rid of the oxygen, we would put 5 moles of O2 on the bottom and 3 moles of CO2 on the top, because that's what we're trying to get to. That will cancel out. Now we are done. So 4.25 times 3 divided by 5. So 4.25 times 3 divided by 5 is 2.55. And you are done. Okay, and hopefully that makes sense if you stop for a second. All right, so in here we have a 5 to 3 ratio, 4.25 to 2.55. So that seems pretty logical, like proportional. All right, type 2, we're going to add on one step. So you'll notice that this last step was just here, and now we're going to extend it to the mass. So mole to mole is a one-step problem. Mole to gram is a two-step problem. But that second step is something we've seen before. So we have a new balanced equation. We're going to be looking at carbon dioxide plus lithium hydroxide gives us lithium carbonate and water, and it is balanced. There's 1 mole for these, and there's 2 for here. So this time we want mass of lithium carbonate, and we're starting with 5 moles of CO2. So 5 moles carbon dioxide. I'm still writing out my formulas, and I encourage you to do that. First step is to do the mole-mole. So we're going to look at our balanced equation. We're going to say, okay, we have 1 mole of CO2 on the bottom, and we're going to lithium carbonate, and we have 1 mole of lithium carbonate on top. Now moles of CO2 will cancel out. Our second step, because we're in moles of lithium carbonate, we want to just go to grams. So we have to use our periodic table and find the molar mass. I've done this many times before. All right, so bring up your periodic table, find lithium. Lithium weighs 6.94. There's 2 of them. So 2 times 6.94. Then we have a carbon at 12.01. And we have oxygen, which is 16 times 3. So that 16 times 3 is, I don't know why I did that. Sixty-nine 30 is 48. So 48 is 73.89. So 73.89 goes on top. Oops. And now we can calculate it. So 5 times 73.89, because the ones are not going to make a difference mathematically. And I get like it doesn't make a difference to put that step in, but it shows like how we go from one, I shouldn't have erased that, one to another. 5 So 5 times 73.89 gives us 369.45. That's going to be 369 because we want to have 3 sig figs. Now this is a much more like practical measurement, because in lab, as you know, you can't measure moles out. So Like, this is the amount of lithium carbonate, in theory, I should produce from 5 moles of carbon dioxide. Okay, I think we have a couple other ones to try. So if you can pause it and try this on your own, that would be best. Use the previous worked out calculation as a model. All right, in this case, we're going to take 7 moles of N2. Okay, that's what we're starting out with, and they want to know ammonia. Ammonia is this, so we're not even working with hydrogen in this case. All right, now we're going to go mole to mole, and then we're going to go mole to gram. So we're going to go from nitrogen to ammonia first. There's 1 mole of nitrogen in the equation right here, and there are 2 moles of ammonia. Nitrogen gone. Now all I have to do is my molar mass of ammonia. So look at your periodic table. Nitrogen weighs 14.01. Hydrogen weighs about 1. There's 3 of them. So that is about 17.04 if you would add that up. Or 17.03. Okay, so that cancels out. Now we're going to just take 7 times 2, which is 14, times 17.03. Oops. So 17. So 7 times 14 times 17.03. Okay. 14 times 17.03 gives us 238.42, but we just want 3 sig figs because we only have 3 here. So 238 grams of ammonia is, in theory, produced from 7 moles of nitrogen. All right, the last one is a different equation again, but same process. So starting with 1.25 moles of aluminum chloride. Okay, so we're going to go from here, and we want aluminum sulfate here. So maybe, I don't know if you're getting confused on what's what, maybe stop and circle them first. We're not worried about these two. We're just working with these two. Pause this, see if you can solve this without my help. Unpause it to see the answer. All right, so we want to get rid of our moles of aluminum chloride. They need to go on the bottom. 1 mole, I know it's a lot of writing, but here we go. Aluminum sulfate on top. This cancels out. Now we want to get our molar mass of aluminum sulfate, which, go back to our periodic table and our calculator, and we have aluminum 2 times 26.98. And remember, aluminum is right there. So, and then we're going to add that. All right, we're going to add that. So aluminum's Al2. Okay, we have 3 sulfurs and 12 oxygens. So 3 sulfurs, 32.07. I don't know, my other parentheses are right there. Okay, and then we're going to add that to 12 times 16. There's 12 oxygens. So 342.17 is our molar mass of aluminum sulfate. Okay, that's going to cancel out. Now we're going to take 1.25 times 342.17 and divide by 2. So we already have that in our calculator, times 1.25 divided by 2. So 214, okay, would be my answer. And that's how much aluminum sulfate we should create in theory.